What is disruption? Disruption is loss of productivity, disturbance, hindrance, or interruption to a contractor's normal working methods, resulting in lower efficiency. Disrupted work is work that is carried out less efficiently than it would have been. If caused by the employer, it may give rise to a right to compensation either under the contract or as a breach of contract. What is productivity? The amount or units of work completed from a certain amount of time. Why is productivity important? It is important to understand what productivity is, so that you can successfully measure the losses. Reasonable estimates will allow you to maximize the payment you will receive for the change. Important note: overrun on labor content can wipes out all profit on the project. Seven categories of productivity factors. Each of these categories has a different effect on productivity, some with direct effects, while others are more indirect. Some will affect the project immediately and others will take longer to have a measurable impact. Project and contract. Location and environment. Project team, owner, contractor, and architect. Managerial actions and decisions during project execution. Disruptive events and signs on sites. Human, worker, reactions. External factors. Project and contract causes are: project size, scope, duration, and budget. Complexity. Project type, hospital or warehouse or commercial or residential. Regulations and building codes. Multiple contracts. Contract type. Construction methods. Special requirements. Location and environmental causes are: transportation network, traveling considerations, logistical support, traffic, and site access. Weather patterns, temperature, humidity, and season variability. Local communities and cities, size, attitude, and economy. Project team causes are: contractor and subcontractor business systems and practices. Project manager, experience, familiarity with project type, time spent on project. Owner, architect, and engineer, construction manager systems and practices. All involved, working, partnership, attitudes, previous working relationship. Managerial actions are the impacts created by the efforts taken by the management when changes happen. Proper actions can minimize the impact. Contractor decisions. Acceleration. Changes in work sequence. Support work, supply of tools, equipment, materials, information, and directives, proper working. Conditions and site management. Ratios of crews and supervisors. Coordination between trades, subcontractors, and shifts. Owner decisions. Change orders. Acceleration orders. Processing of change orders, reviews and approvals. Responding to RFIs, timely and proper engineering support. Timely decision making. Disruptive events. Congestion/trade stacking. Shortage in skilled labor. Increased accidents. Errors, mistakes, and poor quality work. Slower pace, increased breaks, waiting and delays. Stop and go operations or out of sequence work. Bad weather. Rework. Human reaction factors are fatigue, physical reactions to weather or work conditions, disturbed biological clock and sleep deprivation, morale, motivation, and negative attitudes, loss of the job rhythm, social and domestic issues, working without clear direction. External factors are force majeure, unforeseeable conditions, national and global economy changes, political forces and international influences. The learning curve is a good tool to show the decrease in time per unit through multiple repetitions. This occurs because initially the work is slow and gets faster, not because the work begins at full efficiency and goes up from there. This is an important distinction when going forward. When estimating the amount of time to schedule for repetitive tasks, keep in mind that the first few units of the work may be significantly slower than the subsequent units. The rate of learning must be adjusted to the specific type of work being performed. This figure shows 3 different rates. For the first 10 units, learning is beginning and there is a relatively slow decrease in labor hours per unit because the work is still new. A unit can be any part of the work you are looking at, from a door to an entire floor of a multi-story building. For units 10 to 100 there is a faster learning where workers are becoming comfortable with the activity and work is going well, so the labor hours per unit are decreasing rapidly. Above unit 100, the learning rate starts to slow again as you reach the lowest possible time it would take to complete an activity. The slope of the line at each part is the learning rate, and can be changed depending on the type of work being done. There are certain tasks with an incredibly high rate, which will decrease the amount of hours per unit faster. Other tasks have very slow rates because of their complexity, or their characteristics. While the learning curve itself is not a cause of productivity gains or losses, it is important to keep in mind that a worker's hours per unit of work may decrease significantly as he or she does more units of that work. This is important to remember during estimating, and when quantifying the duration of changes throughout the project. Methods of quantifying disruption. This selection process is primarily based on the availability and the characteristics of information available set against the degree of reliability of the quantifying method. Measured mile method selected when physical units of completed works recorded periodically and the non-impacted period was statically significant. Baseline productivity method selected when physical units of completed works was recorded periodically and the non-impacted period was not statically significant and no concurrency between the owner and contractor disruption causes. System dynamics modeling method selected when physical units of completed works was recorded periodically and the non-impacted period was not statically significant and the owner and contractor caused disruption concurrently. Earned value method selected when percentage of completed works was recorded periodically and the physical units of completed works was not recorded. Work sampling method selected when the project records are sufficient but neither the physical units nor the percentage of completed works was recorded. Industry-based method selected when the project records are not sufficient and the disruption cause compatible with industry tables. Code-based method selected when the project records are not sufficient and the disruption cause not compatible with industry tables. Measured mile analysis. The measured mile approach is widely acknowledged as the most acceptable method for calculating lost productivity costs. The analysis compares identical tasks in impacted and non-impacted periods of the project to estimate the productivity loss caused by the impact of a known series of events. It compares actual performance on site with actual performance, not some theoretical planned performance. Measured mile method based on 5 assumptions are: first, there must be a non-impacted or least impacted period, so-called measured mile period, for the specific type of work being assessed. Second, the length of this period should be significant compared to the impacted period and the course of work. It would be unreasonable to extrapolate 2% of progress into 80% of expected costs. Third, sufficient amounts of contemporaneous project data should be available for the analysis. At most, the physical units of work completed have to be periodically recorded so that the cumulative labor hours can be plotted through the course of work. Fourth, the project data are assumed to be error-free. That is, the contemporaneous documentation must be accurately recorded by the contractor. Finally, all disruptions during the impacted period are due to the owner's actions. One selection of the measured mile analyst. Experienced, knowledgeable experts. Understands both construction cost accounting and construction work methods. Review the entire project record. Interview the project personnel, including field personnel. 2. Selection of the impacted period. Graphically plot daily, weekly, monthly productivity over time to identify periods of disruption. Select impacted and unimpacted periods objectively. Compute productivity, not production data. At the minimum, make an effort to demonstrate cause and effect between the changes and the consequences. Investigate the timing of the purported disruptions and their alleged consequences. Ideally, prove what the causes of loss of opportunity were. If unable to prove, demonstrate and explain to a reasonable degree. Make adjustments for non-compensable changes and contractor-caused problems in the impacted period. 3. Selection of the measured mile period. Select a reference period for a narrow spectrum of similar work. Select a period that is similar to the disrupted period as available. Use quantity of work per labor hour as a measure of productivity if possible. If not, resort to quantity of work per % project complete or quantity of work per dollar spent. Consider the means and methods, weather conditions, work hours, project schedule, site logistics, management and supervision, trades, etc. used to perform the work. Consider the managerial aspects governing the works. Select workers with reasonably similar skill, knowledge, and effort. The same labor pool is desirable. Confirm that the reference period has unhindered productivity, both for the contractor and any subcontractors or suppliers. Make adjustments if there are contractor-caused hindrances to adjust the reference period. 4. Calculate the loss of productivity. Test the honesty of the underlying productivity, change, progress, etc. data. Apply loss of opportunity factors to just the time period and labor trade disrupted. Adjust for learning curve productivity factors in the early stages of a project. Adjust for additional labor hours already paid for in change orders. Exclude any loss which is not recoverable under the contract's terms, including contractor's own problems. Look for several different ways to compute a measured mile from the instant project. Report the results using those different ways and bracket them into a high-low range. Consider other reference sources. Other projects by this contractor, other projects by other contractors. Other decisions by this court or board. Check the mathematics, don't present results that strain credibility, such as a measured mile analysis that claims more damages than a total cost claim. 5. Present the analysis clearly. Explain the cause and effect. Focus on key points. Include photographs, other graphic aids, correspondence, job diaries. Corroborate with other methods such as modified total cost, industry guidelines. Rehearse before presenting. Anticipate questions and prepare answers. Tell the truth. To understand what is disruption, we can discuss the following example. The contractor planned to perform paving, on an uninterrupted basis, and to use paving machines for all of the concrete paving except small areas, which were to be done by hand powers. Because of the engineer's changes in lighting and a requirement to put pavement sensing devices in the concrete for a long-range pavement, the work on the south zone was performed on a sporadic and intermittent basis. In fact, much of it was performed on a hand basis rather than using the large concrete slip-form paving spread. This caused a substantially greater cost of performing the work on the south zone than could be reasonably anticipated. The work on the north zone was performed under normal conditions, since the changes were all made prior to the start of work on the north zone and the pavement wear study would not be conducted on the north zone. Cost as a result of these changes can be calculated by comparing the unit cost of labor for the north zone, which were essentially non-impacted, with the unit cost of labor for the south zone, which were substantially impacted. Both the north and south zone were performed during normal paving periods under good weather conditions. The same labor force and the same equipment, with the exception that the slip-form paving spread could not always be used due to the change, was used on both areas. However, the unit labor cost on the north zone, which were non-impacted, was approximately half of the cost incurred on the south zone. The contractor is entitled to be paid $549,155 in additional costs. It represents the best and most consistent productivity the contractor was able to achieve on the project. Neither needs to find non-impacted and impacted periods nor be consecutive reporting periods in the baseline time frame. In other words, the baseline analysis can be more flexible and hence more applicable in current practice. Using individual productivity values is better than cumulative productivity for the calculations. This may be due to varying views on the baseline productivity. The mean productivity of the points falling within the control limits after applying an iterative process of an individual's control chart to deal with different sources of variation of periodically reported productivity values. Determine the baseline productivity as the median of the individual productivity values in the baseline subset. The baseline productivity reflects the normal operating performance of a contractor. SD is widely used in the defense industry. A key feature of SD simulation modeling is that it allows and directs answering a pool of what-if questions such as, what if one particular category of disruptions had not occurred but all others had? What if the owner interventions had not occurred? The SD approach seeks to create a computer model of the project that maps all relationships and feedback loops in a comprehensive dynamic model. Example: computer simulation model to resolve a $500 million shipbuilder claim consisting of the direct impact and the ripple effects between Ingalls Shipbuilding and the U.S. Navy in the 1970s. It visualizes causality and allows for validation of causal logic in quantitative terms and against actual data at any period of the project in dispute. SD modeling has not achieved popularity in construction disputes compared to the measured mile. The earned hours are then compared to the actual hours expended for the period of the impact, and the difference between the two may be used to calculate the productivity loss experienced. Earned value measurement of contemporaneous project documentation, such as percentages complete from schedule updates or payment applications, can assist with calculating labor productivity. It is cautioned that the budget used to generate the earned value metrics be carefully reviewed and verified for reasonableness. Any earned value analysis based upon an unreasonable budget is highly suspect. Can also be used to estimate the cumulative impacts. A fully resource-loaded, labor and quantities, CPM schedule is a good source for obtaining earned value metrics and allows for like-time causation analysis. Work sampling, large number of direct observations and application of random sampling techniques to the study of work activities so that the proportions of time devoted to different elements of work can be estimated with a given degree of statistical validity. From these observations, the claimant determines, on a percentage basis, how much time is spent between direct work, pay item work, support work, moving tools and materials to the work location, or delays, time when no work is being performed. By performing a number of work sampling studies, the analyst can draw comparisons of productivity before and after known events, between work activities or crews, etc. Work sampling has been offered as a means of determining productivity loss, but it can only be performed during the life of the project and is not compatible with a hindsight analysis effort. The contractor estimates lost productivity on the impacted period, and then locates an analogous or similar work activity on the same project, which was non-impacted, and calculates its productivity. The contractor compares productivities during the impacted period and of similar but non-impacted work performed by another contractor on the same project. Are used to contrast the productivities of similar work activities on the project being analyzed and a similar project. Total cost method, attractive to contractors because it assumes they did everything correct. Is rarely used, but sometimes the only path for the contractor. The total cost method calculates damages by subtracting the bid amount from the total actual costs. These are large assumptions that can be very difficult to prove. It is important to remember that if any fault of the contractor is found, the claim can be dismissed. While courts are reluctant to accept this method, they allow it if four requirements are met and proven. These requirements are: 1. Impracticality of proving actual losses accurately and directly. 2. Reasonable and realistic bid estimate. 3. Reasonable actual costs. 4. Contractor has no responsibility for cost overrun. Modified total cost method. It is also possible to use the modified total cost method to quantify a claim. This method is the same as the one described above, except the contractor reduces the amount claimed in order to more fairly represent the damages. This is more likely to be accepted by the courts, but the same four requirements still need to be satisfied. The modified total cost method is very similar to the total cost method, but is more realistic because it removes the assumption that the contractor did everything correctly. It is slightly more work, but also more realistic. Also, there is a greater chance of compensation because it has a more complete picture of the changes that occurred. Specialty industry. Study employs results of specific studies directly related to the cause of damages. Can be about acceleration, learning curve, overtime, weather. General industry. Study is based on industry-wide manuals and/or reports. The industry-based analyses may be employed when there is insufficient project documentation. Used with another method to augment supportive evidence of damages. Quick and inexpensive. The main advantages. Clear and concise data that is easy to use and easy to apply. Data has been agreed upon by a group of experienced industry professionals. No period of unimpeached work is required. The disadvantages to using this method are: additional subjectivity is required by users in determining the level of the condition. Interdependencies between factors must be considered when applying. Multiple losses to the same work, e.g., site access versus logistics. Identifying the affected period of work can be difficult. Different manuals have been created to allow contractors and owner to calculate the anticipated productivity losses due to different factors such as morale, trade stacking, fatigue, and weather. These are only a small subset of the different factors presented, but they show you the range of those presented. Measured mile analysis limitations are: becomes unreliable or even impossible when either a non-impacted period simply does not exist or that period is not sizable. The method is inappropriate for unique and complex tasks. The reliability of the method is challenged if inaccurate project data is used for the analysis. May mask the fact that a contractor generally does not attain a single rate of productivity throughout a time period. Not necessarily reflect the productivity normally achieved by the contractor due to the smoothing effect of successive cumulative data. Baseline productivity analysis limitations are: identified according to the best daily output instead of the best daily productivity. The 10% requirement for the baseline sample size is arbitrary and not based upon scientific principles. System dynamics modeling limitations are: SD modeling has not achieved popularity in construction disputes compared to the measured mile. Earned value analysis limitations are: the percent complete method is not as detailed and accurate. Any earned value analysis relying on an unreasonable budget is very doubtful. Sampling methods limitations are: honesty is not high as they are only a sampled measure of labor productivity. Comparison studies limitations are: definition of similar work or a similar project are rarely agreed by project parties. Industry studies limitations are: their use in calculating lost productivity is not the first preference. Total and modified cost limitations are: successful use of the cost-based methods is limited. Large amounts of change create large amounts of productivity loss, and change orders can cause productivity loss on both the change work and the base contract work. These complicating factors include inadequate scheduling and coordination. Acceleration. Change in work sequence. Late supply of information, equipment, or materials. Increased complexity of work. Effect of change orders issued. The Leonard and Ibs's curves show reasonable estimates based on industry research to allow you to have an idea of what productivity losses your site could be suffering if there are multiple changes or change orders. These graphs are useful for measuring the impact of change, regardless of its type, and have been accepted in mediations, arbitrations, and litigation. For example, during a period of overtime it is possible to have negative weather effects. Each of these factors has an individual contribution to productivity loss, but the combined effect may not be as high as the sum of the two losses.
Free version that you are using is limited to speaking a maximum of 1000 characters. Please upgrade to full version to remove this limitation.
Leonard's curves. Charles Leonard, whose master's thesis is one of the earliest and most widely cited publication on the subject of quantitative impact of change. In that study he collected data from 57 projects and organized it into electrical mechanical work and civil architectural work. Type 1, project substantially affected only by change orders. Type 2, project substantially impacted by change orders plus one major cause of delay. Type 3, project substantially impacted by change orders plus two or more major causes of delay. Ibs's curves improved on Leonard's work, collecting data from 169 large, diverse projects. Projects were larger, included both good and bad experiences, came from 12 different countries and included design phase information. Different delivery systems, different industry sectors, and grassroots and revamp projects were examined. Telephone and in-person follow-up interviews were conducted to verify that the projects were a representative sample of projects. Ibs's analysis used projects more representative of the industry. Ibs also studied the effect that change timing has on productivity. Generally speaking, projects that had most of their change late in the project had lower levels of productivity than projects with earlier change. These graphs are useful for measuring the impact of change, regardless of its type, and have been accepted in arbitrations and litigation. Factors to consider when trying to measure the impact weather may have on your project: type of work, manual or equipment, indoors or outdoors. Type of weather, hot, cold, rain, humidity. Length of weather event, all season or short burst. Severity of weather, extreme heat or cold. The worker's physical condition. Site and material conditions. Motivation of the worker. Wind and wind chill temperatures, sun exposure. Cold weather cause. Inconvenience of weather protection, gloves, extra layers. Hot weather cause of frequent breaks are necessary, loss in motivation. Rain cause. Rapid fatigue, materials, equipment, and soil gets wet, limited visibility, slip hazard. It is clear that there is a more rapid impact for the highest temperatures, but it is important to note that there is a range of 70°F where efficiency will be at or above 75%. With extreme heat and cold there is a dramatic effect on the overall productivity, and in these cases workers' safety should be considered. The only recoverable portion is for unforeseeable weather or events that are unusual and unexpected can be recoverable. Also, for extended periods of heat, cold, and rain, it may not be an option to shut down completely and work will have to continue at a slower rate. Claim for the cost. Disruption to construction work may lead to late completion of the work, but not necessarily so. It is possible for work to be disrupted and for the contract still to finish by the contract completion date. In this situation, the contractor will not have a claim for an EOT, but it may have a claim for the cost of the reduced efficiency of its workforce. Disruption is not just the difference between what actually happened and what the contractor planned to happen. The objective of the compensation for disruption is to put the contractor in the same financial position it would have been in if the disruption had not occurred. Loss of job rhythm, caused by, for example, premature moves between activities, out of sequence working and repeated learning cycles, work area congestion caused by stacking of trades, increase in size of gangs and increase in length or number of shifts. But these are also symptoms of poor site management. The starting point for any disruption analysis is to understand what work was carried out, when it was carried out and what resources were used. Record keeping is just as important for disruption analysis as it is for delay analysis. It is essential for the contractor to maintain and make available to the CA good site records in order that the CA may carry out proper assessments of disruption. The most appropriate way to establish disruption is to apply the measured mile technique. The comparison can be made on the man-hours expended or the units of work performed. However, care must be exercised to compare like with like. It is necessary to isolate issues that can affect productivity but are unrelated to the employer's liability. These issues can include weather, plant breakdowns, dilution of supervision, contractor management, and acceleration. The contractor has an obligation to manage its own change efficiently, and any failure to do this should not be compensated. Unsupported percentage. The use of unsupported percentage additions to assess disruption is not advocated. However, on very simple contracts where evidence of disruption can be demonstrated, this practice may be acceptable, provided that the percentage addition is small. For guidance, no more than 5% on labor and plant. Notice of disruption. The contractor should also be required to give prompt notice of disruption, in order that the CA can promptly investigate the claim variation. Variation. The compensation for disruption caused by variations should be agreed as soon as possible after completion of the variation and where practicable included with the valuation of the variation. Retrospective. Most claims for disruption are dealt with retrospectively. The claiming party must first establish that the event or factor causing the disruption is a compensable risk event under the contract. Sufficient detail is required to isolate the cause of the disruption complained of and evaluate the effects of that. Forms of contract. The contract may also identify if a party expressly accepted certain productivity risks. Standard forms of contract deal expressly with disruption. If they do not, then disruption may be. It is important to understand what productivity is, so that you can successfully measure the losses. Reasonable estimates will allow you to maximize the payment you will receive for the change. Important note: overrun on labor content can wipes out all profit on the project.